So we're going to practice drawing chair conformations for tert-butyl cyclohexane. And just so that we're all drawing the same picture, let's turn that tert-butyl cyclohexane ring such that the tert-butyl group is facing the left. Actually, easier to just do the drawing here as well. I'm going to put a model on the screen. So this is our flat version of the cyclohexane ring with the green bonds. And then the tert-butyl group is the 3 carbons here with the gray bond. And if we turn, so what we're looking at when we drew that first picture is just the flat view. We could add a wedge or a dash here if we wanted, but with only one group on the ring, it doesn't really make sense to. This is the top view, which we think of as the flat view. The side view is what we want to do for the chair, right? And so I'm going to see if I can, I'll use the tert-butyl group kind of as a crutch to hold that in place. And what we're going to do is first draw the bonds here in the back and here in the front that are like along the sides of the chair. And when we say a chair, by the way, what we want to imagine is that this is the footrest. So here's your feet and your legs draped over and your butt sitting in the seat and your headrest, the head up here. It's kind of like a recliner in the reclined position. So we're going to start with a pair of parallel lines that, like the bonds in this ring, slope up as we move from left to right. And we want to space them such that if we connected the top of the bottom one with the bottom of the top one, right, like so, that line slopes about the same amount but in the opposite direction. And so we'll just use that as a template and continue the line here in both directions. And then we're going to take, connect the purple and the green lines, right? So we're going to make the complete chair. If you practice these enough, by the way, you can draw them relatively quickly just simply by freestyling it. You don't necessarily have to do this templating procedure, but in the beginning, it takes some practice, right? And so in the beginning, this may be easier to do. With me so far? Okay, so now we're going to identify the carbon that the tert-butyl group is on, and that'll be this one. It's the right-hand-most carbon. Wow, that doesn't stand out as well as I hoped. At any rate, and that tert-butyl group is that thing axial or equatorial? When we talk about axial and equatorial, what we want to imagine is that the cyclohexane is a globe and it's spinning or sitting on this axis, right? So notice that the hydrogen that's on the carbon where the tert-butyl group is pointed straight up. And next to it, there's a hydrogen that's pointed straight down. Right? And that alternates around the ring. So the next carbon has a hydrogen that's straight up, and the next carbon after that has a hydrogen that's straight down. Does that make sense? So if we, and I'm just going to put some hydrogens on there, or just some empty bonds without hydrogens. And they're going to represent hydrogens too, but it's going to allow us to differentiate. Because notice that, whoops, the carbon next to the one with the tert-butyl group, so if this is number 1, this could be the number 2 carbon, has another hydrogen. Each of the carbons in the ring have 2 substituents, whether they're hydrogens or tert-butyl groups or whatever else. So notice that this one is sloped, and it's sloped a little bit up, but it's not straight up or straight down. This is straight down. These two are straight up. The straight up, straight downs are axial. The ones that are pointed off at an angle are equatorial. Every carbon on the ring has one axial substituent and one equatorial substituent. It also has one substituent that's up and one substituent that's down. And they alternate. So here on this number 2 carbon, the axial substituent, the hydrogen, is down, the equatorial is up. On the carbon where the tert-butyl is, the hydrogen is axial up, the tert-butyl group is equatorial down. So this is going to fit into the mantra, what's up stays up, what's down stays down, but axial and equatorial flip. Now, drawing the things on the ring, and I'm just going to draw some very small bonds for the hydrogens. The axials are easy. So wherever 2 bonds connected to a carbon, as you move towards that carbon, if you slope up, like going from here to the pink carbon, we're sloping up, axial is up. If you're sloping down to get to your carbon atom, then axial at that carbon is down. Yeah. So, and then we alternate, right? Slope up to get to here, slope down to get to here, up, down, right? So then the equatorial positions are going to alternate. So on the dot carbon here, we have axial up, so equatorial is going to be down, but it's not straight down, it's down at an angle. And the angle will be parallel to the bonds that don't touch that carbon. So this carbon has green bonds and orange bonds. The purple bonds are the ones that equatorial bond is going to be parallel to. And that's going to be where our tert-butyl group is, right? And so if we go to the other end, right, that one's going to be parallel to those purple bonds too. This carbon has purple bond and orange bond, but not green bonds. So its equatorial hydrogen is going to be parallel to the green bond, just like this one here that also doesn't have a green bond will be. And then we come to the carbons here and here that have green and purple. Their equatorial is going to be parallel to orange, like so. This is a relatively stable situation because the big tert-butyl group is equatorial. Sorry, that doesn't show up very well. Well, and we say, another mantra we say is that there's more room at the equator, right? So we've drawn one of our chairs, and the chair you drew, by the way, may or may not have looked like this. Because it could be that you just drew it upside down, in which case the tert-butyl group is equatorial up, or it could have been the alternate chair conformation. Because the other thing that we want to do with these is to draw the chair inversion, which is what happens when we undergo a conformational change in the cyclohexane ring. And what happens is we turn the footrest of the chair into the headrest. So I'm going to go through it a couple of times to show you. Let me just put the other axial hydrogens on. So we have 6 axial substituents, and they're all shown, but the equatorial ones are not. Not yet, at least. And I'll go ahead and pull this bond off so we don't see that. Actually, let me put equatorials in 2 key positions. So notice that these bonds are going to be a little bit different because they don't have a hydrogen on them. So it's just the stick with no atom at the end. Now, the conformational change goes like this. The footrest turns up and becomes the headrest. So now we have an intermediate structure called a boat, which is not particularly, it's stable enough that the molecule will spend some time hanging out here, but it doesn't spend a lot of time there. And then what was the headrest twists down and becomes the footrest. And now notice that all of those hydrogens that were pointed straight up and straight down are now up or down, but at an angle, right? They're around the rim or the edge of the ring, which we call the equator. So these are now equatorial. If we flip back to the original picture, everything that's axial becomes equatorial. So what's up stays up, what's down stays down, but axial and equatorial switch. And again, if we go back to the original that we drew, tert-butyl is equatorial down. What's up stays up, what's down stays down, axial and equatorial switch. So when we go to the alternate ring, tert-butyl is still down, but now it's axial. Let's try to draw that structure. And let's first focus on the green bonds that are actually the carbon-carbon bonds in the ring. So we're going to get this same kind of lightning bolt shape, but notice that that pink carbon that we marked here, which is this one, on the first structure it was pointed up, it was the headrest. On the alternate structure it's going to be pointed down, it's going to be the footrest. So let me give you a few minutes and see if you can draw that chair using the same templating method that we did before. The one difference being that the bonds that we start with are going to slope the opposite direction. And when we do draw these, by the way, we want to make sure that their ends match up so that they end the same place vertically. Mine got a little bit twisted and a little bit off, but start there, and then we'll go through the same routine. And I'll go ahead and start drawing while you're drawing. I'm going to pick the other color to template this time. So connect the bottom of the top one with the top of the bottom one. And we draw that connection, continue that out, try to thicken up that line so you can see it better. Try to draw these a little bit longer too, so the picture ends up a little bit bigger. And then again, if we want to use multiple colors, we can, or we can simply do this in one. Then we connect the ends of those lines so that we get the lightning bolt shape, like so. And what we want to appreciate or acknowledge is that this carbon that's at the tip, little Rudolph the pink-nosed cyclohexane, is still on the left-hand side. So we haven't done this, right? We've kept all the atoms in roughly the same space or region of space, and we've just done this conformational change where they've adjusted themselves relative to each other. We haven't spun the molecule around or flipped it upside down or anything like that. So now, and one of the tricks, by the way, of visualizing this is to try to see how the picture that we drew matches that molecule, which isn't a perfect match, but we're hoping to visualize that the purple bonds we drew first are this one and this one, and that the orange bonds we drew next are this one and this one, and then the green ones would be this one and that one. Now, since we slope down to the pink carbon as we approach it, our axial group there is down. What's down stays down, so that's now where the tert-butyl group is, right? And the hydrogen that was on the carbon with the tert-butyl group stays up, but it's now equatorial. What's up stays up, what's down stays down, but axial and equatorial switch. And of course, we're drawing this as a skeleton structure, right? If we wanted to draw C's with H's, what we want to acknowledge about the tert-butyl group is that it's giant. And it's a lot of atoms all clustered in together. Now that we've got the alternate chair, we're going to add the energy consideration here. Which of these two is more stable and why?